She has done her PhD at IIT Hyderabad and currently she is doing her postdoc at PRL. So today she will talk about probing compressed inert scalars with forward muon tagging at the Muon Collider. So over to you.
Thank you, Chanchari. Thank you, professors, for this invitation and giving me the opportunity. Giving me the opportunity to present my work here. So today I will be presenting probing compressed inert scalar with forward muon tagging at the Muon Collider. So this is based on this archive entry and this work has been done with collaboration Anupam Ghosh, Professor Partha Konar and Bhavya. So the main focus of this talk is how to exploit the clean environment of a Muon Collider to probe the compressed inert scalars and with the vector boson fusion production processes. So first, in the introduction, I will motivate the BSM physics with the motivation of dark matter studies and how to probe the compressed mass spectrum in a BSM scalar at a multi-TV Muon Collider. The main production processes will be with the vector boson fusion processes, and which in the high energy Muon Collider it is the most dominant process that I will discuss. Then what is the advantages of Muon Collider over the LHC, and how the forward muon tagging will be very effective in case of probing this kind of signature which is otherwise elusive in current LHC. And our goal is to probe the inert doublet model. We chose this model to see the signatures at multi-TV Muon Collider. We did the cut-based analysis as well as using XGBoost, the ML analysis also, to increase the signal sensitivity. And finally, I will conclude with the take-home messages. So standard model is very effective to explain the gauge theories, but standard model cannot accommodate most like some of the physical phenomena that are observed. Mostly like it fails to account for most of the matter content of the universe, that is like 85% of the total matter content that is lying as a dark matter. Standard model cannot accommodate that. Standard model has no stable neutral non-baryonic particle that can serve as a dark matter, but so many astrophysical observables which are independent to each other are there, like to show us that dark matter may exist in our universe. So first of it is the galaxy rotation curve. So what is it? If you observe any spiral galaxy and if you measure the velocity of any star very far from the galactic center, you may calculate that with the distance the rotation velocity will decrease. As in the solar system also, you can see that the planet very far from the sun, the orbital velocity of that decreases. But what we observe is this is the observation. It is almost a flat rotation curve. So that means there is some unseen non-baryonic matter. Some unseen non-baryonic matter that is pulling those stars gravitationally, or that is acting gravitationally. Second is the gravitational lensing by Einstein's GR. You know that if there is some massive object, the light bends across it. So like we can observe like much more strong lensing in some galactic center that may accommodate some dark matter. Third is some from the W map or Planck this CMB temperature graph. You can incorporate some of the dark matter. You can incorporate that there must be some dark matter present, cold dark matter present. So before jumping into some model, first I will say that like what is the most convenient theory for the production of the dark matter at the early universe. So let's say if you see this figure, let's say a dark matter of mass 1 TeV, for example I am saying dark matter mass of 1 TeV is initially with the thermal bath with the standard model particles, and what it will do, it can annihilate to each other, it can interact with each other and annihilate to standard model particles in the early universe, and it can it can be reproduced by the standard model interactions also. But as the universe expands, the annihilation rates got decreased, and at some point the annihilation rate, this gamma annihilation can be smaller than the Hubble constant or Hubble parameter. So at that point, what will happen? What happened? Like the dark matter particle could not find any other dark matter particle to annihilate, and at that point, actually, the relic density of the dark matter can be constant. That is the point of the freeze out. So this is the freeze out mechanism. The measurement of the current relic density by Planck is omega h square equals to 0.12. So here, if you see the rate curve, a red dash curve, it has the smaller smaller annihilation cross section. So it says the late freeze out, so it gives the overabundant signature, and the blue dash curve has the large annihilation cross section. That means the annihilation is very efficient, and it can give the underabundant. That means from the current relic density, the relic density will be smaller than that. And this green curve is basically the correct relic density given by Planck. So let's say, so we understood that standard model does not incorporate any of the dark matter particles, so we can extend the standard model. So one of the minimal way to extend the standard model is adding one scalar doublet, scalar SU2L doublet, that is this phi 2. The components of this is like H plus, H0 and A0, and the hypercharge of this scalar doublet is half. So if you impose the Z2 symmetry here, and if you say that all the standard model fields are even under this Z2 symmetry and this phi 2 is odd under this Z2 symmetry, then this phi 2 will not interact with any of the SM fermion, and this will prevent the efficiency, and it can ensure the stability of the dark matter component. So this is the CP conserving renormalizable potential if you incorporate the phi 2 with the standard model particles. So here you can see this lambda 3, 4, 5 are the Higgs boson couplings, and lambda 2 is the extra self coupling of the phi 2 scalar. After the electroweak symmetry breaking, you can get 4 extra scalar particles. One is CP even neutral scalar, one is CP odd neutral scalar, and a pair of charged scalar. And your standard model Higgs is there. And the mass for this H0, A0, no, standard model Higgs is small h, that is not written here. Yeah. This is from phi 2 which scalars are coming. Yeah. And the masses of the H0, A0 will be given by this, and here this is the combination. So this coupling is basically the effective coupling, the combination of lambda 3, 4 and 5. The plus combination will give you H0 and the minus combination will give you A0. And this is the mass of the charged Higgs, and which is only dependent on the lambda 3. Here in this work we assume that lambda 5 is always less than 0. That implies that the mass of H0 will be always less than the mass of A0. So here in this case the H0 is the most stable neutral particle which can incorporate the dark matter candidate in this model. These couplings are real. So as we have seen that this IDM can provide a minimal testable dark matter framework. Here H0 is the stable neutral particle, and the inert scalars does interaction with Higgs only via the Higgs boson coupling, and it can interact with the gauge bosons via the gauge coupling. And only these two types of coupling makes the model very simple and predictive. Here we have focused on the compressed mass spectrum. Compressed mass spectrum means the mass difference between the BS and scalars will be very small. That means the mass will be mass of H0, A0 and MH plus minus are almost similar. So the motivation of taking the compressed mass spectrum is this ensure the efficient co-annihilation, and that can give you the correct relic density, and it satisfies the electroweak precision observables like these STU parameters. But the main problem of probing the compressed mass spectrum is that, let's say here if A0 decays to H0 and L plus minus, since the mass difference between A0 and H0 is very small, the produced L plus minus will be with very low momenta. So you cannot tag these lepton pairs or the jet pairs or lepton neutrino, any of these decay components, decay standard model components at the LHC, because it will give you, it will be coming with very soft PT. So this is a problem to probe this kind of compressed mass spectrum in the LHC. That is what we want to probe this model in the future Muon Collider. It can give a very clean environment, very minimal QCD background, and the efficient forward muon tagging from the VVA production processes can give very clean signature, and it is ideal, the Muon Collider will be ideal to probe this heavy inert scalar with compressed mass region. Okay, so before going to the collider study, let us now find that what is the parameter region that is accessible from the dark matter relic density indirect and direct detection experiments. So this is the parameter scan for the relic density calculation, and in the x-axis the mass of the dark matter is there. So here we have considered the Higgs portal coupling lambda h, which is the combination of lambda 3, 4 and 5 from 0 to 0.5, and the mass difference between the two neutral scalar and the charged scalar and the heavy scalar is in between 0.1 to 15 GeV, and this mass hierarchy is maintained throughout this talk. Will be maintained throughout this talk. That is, the mass of H0 is less than the mass of H0 and is less than the mass of H plus minus. So this is the main annihilation and co-annihilation channels that you can see that can incorporate the relic density. So H0 going to SM. This is via Higgs portal coupling, and this is the co-annihilation. So in case of the compressed mass spectrum, the co-annihilation dominates, and the relic density if you can see this plot, the relic density increases with the increase of the mass of the dark matter particle, and if you lower the lambda h, the relic density will be getting lower, because the cross section here to calculate the relic density is directly dependent on the lambda h. So if you increase the lambda h, the cross section will be increased, and hence the relic density will be lower, will be smaller. So that from here you can see that the correct relic density or the observed relic density can be obtained starting from the 550 GeV of the dark matter, and you can get it up to 1.1 TeV of the dark matter mass. So
I have seen people have not this, people have compressed SUSY LHC. So why can't you go compressed IDM LHC?
No, compressed SUSY, actually we targeted the mass gap up to 15 GeV. Okay, so if it is like up to 15 GeV, then we have simulated that the coming L plus L minus, like if you consider this decay, and the coming L plus L minus is very soft. It is less than 5 GeV, like most of the events with lepton pairs are having PT less than 5 GeV. So that is difficult to probe. But like if you say that compressed mass spectrum, but if you increase it up to 50 GeV, the mass difference between these two particles, then you can achieve like leptons around 20 GeV, like 15 to 20 GeV. Then yes. But like with very compressed mass spectrum up to 15 GeV, it will be difficult. So as we have seen that the effective lambda coupling for the coannulation depends on the lambda H parameter and the delta M parameter. So here we have changed the lambda H parameter from 0.5, 0.25 and 0, keeping the delta M plus minus around 1 GeV. So if, this is the proof that if you increase the lambda H, the relic the cross section will be more and the relic density will be less. And so in the next plot we have fixed the lambda H value at 0, and we can change the delta M parameters like this, and we can get different relic density satisfied region for different mass of the dark matter particles. So here we have varied both the we have fixed lambda H at 0.5 and we have varied the delta M plus minus and delta M 0, and you can see from the second plot to third plot the whole region is got shifted down. So that is because the effective coupling is getting larger in case of the third plot than the second plot. So the previously I have discussed the relic density satisfied region and the parameter space that you can get from that. So now after discussing that, we will come to the detection prospect of the dark matter candidate. There are three independent detection prospect. One is the direct detection. Okay. Yeah, this is the This is the coannulation.
Yes.
This is the. Okay. So first is the direct detection. Here, here the dark matter particle, if it annihilates, if it collides to some SM nucleus, it can give some recoil energy that we can measure in some ground-based experiment like Lux Zeppelin and Xenon 1T. That is, if we can get any excess, then that can be a probe of the dark matter via the direct detection process. In case of indirect detection, in the galactic center or like if the dark matter is present and if the dark matter is annihilating to some SM particles, let's say some gamma ray photons, some neutrinos or some positrons, the excess can give you the signature of the dark matter via the indirect detection. The experiments like Hayes, Fermilat are looking for this. And the third one is the collider, so collider probe. So in case of the laboratory at LHC or at any kind of Muon Collider or any leptonic collider, from the SM particles you can produce the dark matter particles. So dark matter particles will not be directly detected to the collider, the detector, but like it can give you some missing energy signature which if may not be explained by the standard model neutrinos, that can indirectly say that some dark matter particle we can find. Sorry.
The question was, if you fix that lambda H, then what are the other parameters with which you were varying the mass difference?
If you fix the lambda H,
How you were varying the mass difference between H, 0 and this one, which are the other parameters?
okay, so lambda H, okay, coming to the this expression. So let's say here lambda H is basically lambda 3 plus lambda 4 plus lambda 5, let's say, and here lambda 5 is negative. Okay, so like if you keep the lambda H fixed, and if you change this lambda 4, 5 in such a way that this plus combination is fixed but the minus combination is changing. You understood? So let's say you vary these three parameters lambda 3, 4, 5 in such a way that the plus combination is giving you fixed but the minus combination will be changing.
Lambda 5
Yes.
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 How many three parameters we have?
So like if you say like lambda 3, 4, 5, these three, and basically the mu, that can mu 2.
But mu 1?
Mu1 is fixed because it can give you the standard model Higgs mass.
Oh, 5.
Phi 1.
Lambda 2 is also
Lambda 2 is a free parameter, but it doesn't incorporate anything in the cross sections or the mass. So, like you can fix it or vary it, like up to you, but it won't give any effect. Okay. So, this is the scaled spin independent cross section varied with different masses of the dark matter. So, here the most stringent bound for the dark matter direct detection you can see from the Lagzeppelin 2024 data. This is the neutrino floor, it is not a bound, but if the cross section is lower than this value, then the dark matter can be mimicked by a neutrino. So, this is one kind of bound kind of thing that people does consider. So, from here you can see that the lambda h value that is less than 0.02 is under neutrino floor, and the highest lambda h value that we can get is 0.002 is under neutrino floor, and we can get up to 0.05, I think, that I will show in the next plot. And the relic satisfied point is the deep blue points, and the mass is of greater than 500 GeV is in the relic satisfied point, and from here we chose two benchmark point. One is with around this mass 550 GeV, and another one is a slightly higher mass. That these two benchmark points will be validated from the relic density calculation, direct detection, and also the indirect detection cross section. Yes. So, here so up to now we have seen that the higher lambda h or the higher.
Sorry, both these benchmark points satisfy the relic density.
Relic density. Yes. So, if I show you this figure, this table. So, if you can see that the benchmark point 1, which is around 550 GeV, has the mass difference between the neutral components is around 1.11 GeV, and it satisfies the relic. And the second benchmark point, that is coming around 724 GeV, that in our parameter scan we got the highest mass that is possible, which satisfies the relic density as well as the direct detection and indirect detection bound, that is like 725 GeV around, and the mass difference between the neutral component is 13 GeV, and the charge component is also around 13 GeV, and the lambda h in this case is around 0.02, and the lambda h for the benchmark point 1 is even more smaller, that is like 0.003. Okay. So, this is the setup for the collider, this is the setup for the collider. Now, we will see that why Muon Collider, we can study this model in the Muon Collider rather than LHC. So, this will show that the Muon Collider excels over the LHC for this IDM scenario. At the 14 dB LHC, or even if it's very near future upgrades, that is like with let's say 27 dB or something, or even if with high luminosity LHC, that is HL LHC, both the production rate and the detection prospect of this model with very compressed mass spectrum is limited. And Muon Collider, in Muon's particles are basically a point-like particle. So, unlike proton, here muons do not suffer the pattern distribution function. The entire center of mass energy is available for a mu plus mu minus collider, which enables the efficient production for a heavy BSM particles. And in a Muon Collider, the Muon collision produce very minimal QCD background. It is basically hadronically clean environment, and it aims to be a very high precision, high luminosity discovery machine for the BSM particle searches. So, here this plot is taken from this paper. So, here you can see that for the electroweak processes, if you see the orange dashed line, so the cross section that we can achieve from a 100 TeV PP collider, we we can get the similar cross section for the electroweak processes for a 7 TeV Muon Collider. And for the QCD production processes, the energy we require here is a little bit more, that is 14 TeV in case of Muon Collider. So the basic theory is that, so what is the physics that 100 TeV FCC-HH can gain, the 14 TeV Muon Collider can achieve the similar kind of cross section. So the setup here we considered is the 10 TeV Muon Collider, 10 TeV center of mass energy Muon Collider with the luminosity of 10 autobahn inverse, and we can see in the next slides that few slides that it is ideal for probing the inner doublet model with compressed mass spectrum for a 1 TeV and beyond mass. So these are some very highly cited and my favorite papers that I have listed, which came in between 2020 to 2023. Some of the papers are really very famous, like the WIMS at high energy Muon Collider, let's say the vector boson fusion at high energy Muon Collider, the Higgs self coupling, the displaced vertex for the sterile neutrinos in the future lepton collider, the electroweak coupling constant probe, the invisible Higgs from a forward Muon Collider, and searching for leptoquarks at future Muon Collider and all. Next, I have listed one of our work in my PhD thesis, that is like probing inert triplet model at a multi-TeV Muon Collider via vector boson fusion. Here we have considered like the disappearing charge track and 2 forward muons in case of a multi-TeV like 6 TeV and 10 TeV Muon Collider. So coming to a very unique detector design for a Muon Collider is that, like unlike the hadron colliders, Muon Collider has negligible QCD background, but it suffers from sufficient beam induced backgrounds. So beam induced backgrounds are basically the soft photons, electrons and hadrons that dominantly coming from the muons while flying, and it can accommodate in the region with eta greater or equal to 2.5. So to incorporate or to absorb this BIBs or the beam induced background, they propose that one tungsten nozzle can be here in the region greater than eta greater than 2.5, and basically this tungsten nozzle can absorb all those BIBs such that it cannot affect the actual detector components in case of the Muon Collider detector. But the forward muons which can come from the vector boson fusion processes will be high energetic, that can penetrate this tungsten nozzle and can be detected a forward muon detector placed somewhere like here. So this is basically the detector cartoon diagram for the Muon Collider. 2 detectors are there, MUSIC and MIA, those are proposed. So MUSIC is muons measure for interesting collisions, and MAIA is basically muon accelerator instrumented apparatus. So you can see that this sky color region is basically the tungsten shielding here, and wrapping the interaction point, you have the ECAL, HCAL and the muon detectors in both of the cases, both of the proposed detectors. So till now I was saying that we will probe this model via the vector boson fusion processes, but not the S channel cross section processes. Why this is so? Because in case of the S channel process, the cross section falls over 1 by S. So if you see, if you go with very high energy, so it will be a 1 by S separation. But for the vector boson fusion processes, the cross section grows over log square S by mw square. If here you can say mw or mg square depending on which gauge boson you are giving here. So this is the cross section diagram here for your understanding. So if you see that starting from this is like with the particle pair production mass of 1.8 TeV, let's say around 2 TeV. So if you increase the center of mass energy in the Drellian cross section, it drops out, but in case of the VVF production, the cross section is increases by this formula, it is log square S. So that is what in a multi-TeV Muon Collider, if you go for the higher cross section, the VVA production processes is basically dominated over the S channel processes. That is what we are. Mu, okay, I have the Feynman diagram. Let's say here. So if it is W, you cannot get this muon. So it's via Z boson, and these are the vector boson fusion processes. I'll come to this diagram just. No, if it is W can be there, but if it is W, it will be neutrino. So we are interested to tag these two forward muons. That is what we did not incorporate W, but W can be here. If you are not doing the forward muon tagging, W can be here. If it is W, here will be neutrino.
Yeah, but that will be weaker because the missing energy. That will be weaker because the missing energy.
No, I will tell you why the missing energy also won't come, because like you are pair producing, since these are the dark matter particles, you have to pair produce this. So if you are pair producing, the missing energy will cancel each other. So it won't be the high missing energy that you can give from some dark, that like you can say this is coming from some dark matter particle. A0 decay to H0, L plus L minus, and those L plus L minuses are very soft. So in the central region, in our case, exactly. So we will tag the two forward muons here. Nothing else. H plus also will decay to H0, L plus nu. Same problem. So one more aspect is there is basically the like the beam energy resolution in case of the Muon Collider. So the beam energy resolution quantifies how precisely the detector can measure the energy of the final state particle. It is basically defined like this, delta E by E. So from this figure you can see that if the energy resolution is lower, let's say 10%, then like any of the observables, you cannot construct a delta function kind of peak. The peak will be very much broader. If the energy resolution is small enough, that is like for the good resolution, you can construct any of the observable like very precisely. So later as we go, we will see that in case of the Muon Collider, the energy resolution of the initial beam is very much important to probe some BSM physics. So here, as we have telling that our final state will only incorporate two forward tag muons. We will pair produce the dark matters, and if we produce A0 or H plus H minus, the decay products of the SM particles which will be coming from H plus minus or A0 will be soft enough to be detected. Yes.
So here, why can't you emit the Z from the final state and make the Z? Oh, but there is an offset because the Z will decay to. No,
Can I draw in the board?
No, I'm trying to produce this A0 or H0 from a final state brainstorm. That will not happen. The energy will not work. Yes, Muon will emit a Z. Muon will emit a Z. And then so it's offset Z. I think the offsetness will kill it.
Yeah, the cross section will be probably
yes. So
dropping.
I was get a photon, so it's cranking the cross section, emitting a Z. Then it will not work.
So there also, like if you produce A0, it will eventually decay to H0 and L plus minus. Since the mass difference is very small between A0 and H0, those L plus minuses also will be soft enough to be detected. Of the? So A0 decay, so here in this case it is coming less than 5 GeV, because like we considered very compressed mass region identified, but few events, like only few events are coming like that. But can you really trigger the event with very soft leptons? Yeah. Here the trigger is the two forward muons. Two forward muons. You can still identify. Yes, 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 yes.
So your only signature is the muon spectrum.
Yes.
Final state muon spectrum.
Two forward
Yeah,
muons.
two forward.
Yeah. And okay, so let me just explain this diagram. These two are very easy, you can understand. This is one Higgs boson diagram. So this coupling, this Higgs to H0, this coupling is dependent on this lambda H that I have discussed. And this is one vector boson fusion kind of diagram only, but mediating via one A0 and H0. This is also same for the H plus minus. So here this mass hierarchy is again maintained.
So this one, because question here, I mean, for a given H0 and A0, we know the muon energies, right?
Yes.
So then can't you, so I know the A0 is producing soft leptons, but can't you correlate that right for only if the muon energies are in this range, you can tag it. That will be better.
Yeah, but pair production is there. So like I think 4 leptons will be coming.
Yes.
Some of them will be mistagged. Like 4 lepton tagging efficiency is very less. Like will be less with very small PT, right?
Yeah, that's what I Yes, then you, because this
No, then actually, okay, I will come to the background then.
then it will be a signature of this process, right? Otherwise, it's technically it's not a signature.
It can be anything.
Yes, exactly. It can be anything. You're just doing an energy conservation, right? But if you tag that thing, because you know the muon energy has to be like this, then it can be it's not a signature, it's a better thing, right?
But like what we have simulated, like very few leptons, like the tail is coming up to 5 GVPT. Okay, most of the leptons are coming like in between the zero, I mean the zeroth bin only. So the tail is like coming up to 5 GB with very low number of events where this background is killing basically those events. If you produce mu plus mu minus going to 2 forward muon and W plus W minus, these W's can give you 2 leptons. If it is decaying leptonically, it can give you 2 leptons, and this background was completely killing those events.
So it's an absence of leptons. Actually, you are using the absence of leptons in the central region.
Yes, absence of anything in the central region, only 2 forward muons. I can do it with electron, but with high energy electron collider is not possible because of the radiation, synchrotron radiation effect. The muon mass is 200 times larger than the electron mass, right? So the radiation will be dropping by 200 to the power 4, that order. So like having a 10 TeV electron collider is absolutely not possible. So till now I think they could probe up to 350 GeV lepton collider. They can go up to 500 GeV lepton collider, but 10 TeV is absolutely not possible. Okay, so some more criteria about the forward muons. So to tag the forward muons, the eta of mu f1 and mu f2, the production of the eta will be less than 0 because they two will go in to opposite direction. And the tagging the forward muon is basically like the eta will be in between 2.5 to 7, because in that region only the forward muon detector will be sitting. If the muon energy is greater than 500 GeV, then it is 100% sure that the muon can pass through the tungsten nozzle and can be detected to the forward muon detector. So that is what we put this card, but you can lower this card, but then you have to multiply it with the forward muon tagging efficiency. It won't be 100%. And we kept that the energy of the first muon and the second muon, like the mu f, this will be mu f1 and mu f2 is less than 10, less or equal to 10 TeV, since we are doing the 10 TeV muon collider. So these are the possible backgrounds in case of our signal, only tagging to forward muons. Here, since we are seeing for completely clean signature in the central region, this background is very much dominated, and it is basically one irreducible background. It also will give you two forward muons plus missing energy, and it can come from the Z and W boson fusion processes, and the kinematics for this background is basically identically similar to the IDM signal that we will see in the next slides. So this is one more diagram. If the W bosons are decaying leptonically and those leptons are like not tagged or mistagged, then this can be also a background here. Mu f to ZZ is also a background when these two Z bosons will decay to the invisible particles, and for that the branching ratio is actually 4%. So this is not that much relevant, but we considered this. Another background is mu plus mu minus Higgs, and Higgs if it is decaying to invisible. So this is also another background. So these four SM processes, basically the first one can mimic the IDM signal topology, which is like two forward muons plus some missing energy can be there, but it's not a high missing energy, and the background separation is very crucial in this case. So these are some kinematical observables that we can calculate, and we can put some cart on this kind of features or parameters. That is, first is the invariant mass of these two dimuon system can be calculated like this. The delta eta separation or the pseudo rapidity separation between two forward muons, the transverse momentum of the muon pair, that is calculated like this, the azimuthal angle separation, the missing invariant mass.
I think Z to Lulu is more than
No, I am saying like the both Z. Both
so
Z.
it's not an individual.
Exactly.
Yeah.
The
Yeah.
two Z's are there.
Yeah.
Both Z going to Nuremberg.
Oh, you said both. Sorry, I missed it. Sorry.
Okay, so I am also sorry if I missed like both Z going to Nuremberg. Okay. So this is the missing invariant mass, can be calculated like this, and the minimum muon energy also we have taken to put some cards and to distinguish the signal from the